Recall that with related rates, we're always talking about some sort of shape changing with respect to time. So it might be the actual solid that is changing. So maybe we have a cone that is increasing or decreasing in size, or maybe we're talking about the liquid or substance inside of a container growing or shrinking in volume, something like that. Since we are talking about change with respect to time, this is always going to involve taking the derivative of that formula, whatever formula we're using. And when we take the derivative, we're using implicit differentiation, and we'll end up with whatever variable that is, dt every time. So for the right side of this, remember that 1/3 pi can be on the outside of the whole thing, or you can include it in both parts of the product rule. Taking the derivative of r, I get dr dt times h plus dh dt times r. We could be talking about a 2D figure, so in this case the area of a circle, when we take the derivative, we will get this 2 pi r dr dt. Or another common one is looking at a right triangle, so maybe a ladder leaning up against a wall, and using Pythagorean theorem to say that our x is going to change in this way, this 2x dx dt plus 2y dy dt. And then because c is actually the length of the ladder, it will be a constant, so our derivative there will always be 0. And in this case, our dx dt is that change in the distance between the wall and the ladder, the bottom of the ladder. Our dy dt is this distance between the top of the ladder and the ground. So your dy dt is typically going to be a negative because it's that rate of the ladder falling. So since it's going down, that's a negative rate. So our first step in any related rates problem is just identifying any information that we're going to be using, what it represents, and then also any formulas that we might need. And sometimes they give you a formula, like for this example, they did tell us the volume of a sphere, the formula for that, so we'll note that. But it also involves circumference, so that's one that I'm going to have to know. Circumference is 2 pi r. So in this example, we're talking about a water balloon that someone is throwing at a pedestrian. Don't do that. The balloon is filled at a rate of 4 inches cubed per second, and then it wants to know how fast is the radius increasing when the circumference is 6 pi inches. Okay, so each number here is going to tell us something. So let's start with this 4 inches cubed per second. And the units should give away what we're talking about. Since it's cubed, that means we're talking about volume. But since it's per second, that means that this is dv dt. Is this 4 inches cubed per second? I'm just going to say 4. We're also given the condition, so this isn't always true, but we're talking about the specific time when the circumference is 6 pi, which notice if I plug that in, that's going to help me find the radius at that condition. And then we're looking for how fast the radius is increasing. So what we're looking for here is dr dt. So hopefully we can kind of see if I take the derivative of this, I'm going to be left with the dr dt in there that I'm looking for, but I'm also going to have the radius that is unknown and the dv dt that's unknown. So I'll be plugging in my dv dt. I can solve for the radius and plug it in as well, and then use that to find dr dt. The second and third step here go hand in hand, and it's really before you take the derivative, or maybe you take the derivative in your head, so just thinking through taking that derivative. And if there are too many variables left when you take the derivative, then you need to back up to one of these things. So it could be that one of the variables there is a constant. So we're talking about that ladder earlier. We need to put in that length before we take the derivative because it will not change. Same with something like this, where our container, for example, is a cylinder, and we've got a liquid in there that is either rising or falling, and the radius of this container and that volume of liquid is never going to change. So it's not in a cone where the radius depends on how high the level of the liquid is. For this, say the radius is 5, the radius is always going to be 5. So I need to back up, and before I take the derivative of the volume, I would plug in that 5 for the radius. The other thing that we might need to do if we have too many variables is replace one of those variables, not with a constant, but with something in terms of the other variable. So for example, I've got this cone that has a 6-inch centimeter diameter and an 8-centimeter height. The cup is being filled at this rate, so we've got dV dt is 4. And then it wants to know the rate of change of the height of the liquid, so we're looking for dH dt when the height is 5. Okay, so if we think through taking the derivative here, I will have to use the product rule for that r squared h. So that means that I'm going to have an r, an h, a dr dt, and a dH dt, as well as my dV dt left, which I can plug in 4 for that, I can plug in 5 for the h, but now I'm left with the radius and dr dt that I don't know, and I'm trying to find dH dt. So if I could back up and replace the radius, then I can take the derivative and it's not as bad. So the way that we want to replace the radius is just using the fact that wherever the height of my liquid is, it's still going to have the same proportions of the cup. So if my radius to my height of this is 3 to 8, that's going to be true no matter what height that liquid is at. So I can go ahead and solve for the radius by cross multiplying and getting that my radius is this 3/8 h. So if I replace my radius with 3/8 h before I take the derivative, now I can solve for my dH dt. And then our last steps follow pretty easily. We're taking the derivative, make sure you use implicit differentiation, and if it's a variable m, then it should have a dm dt next to it. We're plugging any known rates, any conditions, when this is happening, something like that. And then our last thing is solving for that unknown. So in our first example, we're given the radius of a circle that's increasing at a constant rate, 0.2 meters per second. And then it wants to know what the rate of increase in the area of the circle is at the instant when the circumference is 20 pi meters. So my first step, just getting out all of that information. This 0.2 meters per second was dr dt. It wants to know the area of the circle, the rate of increase of the area, so dA dt is what we're looking for. And then they also tell us the condition is when the circumference is 20 pi. So I'm also going to have to add in my knowledge of circumference being 2 pi r. So if I think through the area of a circle and taking the derivative, my only variables will be dA dt, which I'm looking for. I'll have the radius, which I can solve for using this, and then dr dt, which I'm given. So I'm okay to go ahead and take the derivative. And even start plugging in things that I know. I'm looking for dA dt, so I'll leave that. I've got to solve for the radius, so we'll come back to that, and then dr dt was that 0.2. So in plugging in the radius, I just need to use the fact that my circumference is 20 pi, and then circumference is 2 pi r, so if I divide by 2 and by pi, I will get that the radius is 10. Now it's just a matter of plugging it into the calculator. My answer is in terms of pi. We should get 4 pi, and this was meters squared per second, because we were talking about the rate of change in area. For this next example, I do want you to see how much of this you can get through on your own, but we're going to look at one part at a time. So go ahead and read the prompt and attempt part A. So before I even get started with part A, from the prompt I can get, okay, this is a cylinder, but it's going to be pretty low to the ground, so kind of an idea of what that oil slick looks like. We're given that 2,000 cubic centimeters per minute, so that's the dV dt, how that volume is increasing, and then the formula for volume of the cylinder. And then when we get to part A, it's got a lot of information in it, but really with related rates, that's good news. They tell us the condition is the radius being 100 and the height being 0.5. They also tell us that the rate of the radius increasing is 2.5, and we're looking for that rate of the height increasing. So when we take the derivative of our volume, we should get this dV dt equal to blah. Make sure that you use the product rule here and that your pi is either left on the outside or it's with both of these. So you'd have a pi here and a pi here if you did not have it on the outside. Once we start plugging things in, we realize pretty quickly that we've kind of got it made from here. That we're plugging in everything, nothing is missing except for what we're trying to solve for, that dH dt. I'm probably going to need a calculator here. I went ahead and divided both sides by pi so that I didn't have to mess with that. The simplifying to 250 and the 10,000 there, subtracting 250 over and dividing by 10,000 to get dH dt. And then remember, you can leave it gross like that, or you can go ahead and put it in your calculator. Make sure you round to 3 decimal places if that's what you choose to do, and you'll have centimeters per minute. Go ahead and pause the video again, see what you can do with part B. So in part B, we're given the fact that now we've got this device removing the oil at this rate of 400 radical T cubic centimeters per minute. We still have it flowing out at 2,000 cubic centimeters per minute, and it wants to know the time that the oil slick reaches its max volume. So remember, when we're talking about maxes, we can take the derivative of whatever we're talking about. So if we take dV dt and find where it goes from being positive to being negative, that's where a max is occurring. So the hardest part of this one is just deciding that dV dt is going to be that rate that it's flowing out minus the rate that it's being sucked up. You do have to be careful here. If they didn't give us a rate and they just gave us like the equation for the amount that's being taken out, something like that, then we would go ahead and take the derivative so that we would have the rate. But from here, we're setting it equal to 0 because it does have to change from positive to negative at a 0. Subtracting my 2,000 over, but then dividing by negative 400 gets us 5. And squaring tells us 25 minutes. And we do want to be sure that it changes from this positive to negative. So my next step is just to analyze that graph a little bit. And we could plug in a value to the left and the right of 25 to see that this does actually, it's positive on the left, negative on the right. But also, this is just a radical function that has been shifted up 2,000, and then it's negative, so it's going down from there. So our knowledge of parent functions would help us really quickly right there to see it is going from positive to negative. We want to make sure when we explain that we say we know it's a max because dV dt went from being positive to being negative. Okay, last part, go ahead and pause the video to try part C. Be careful here that you're following directions because they want you to write, not evaluate the integral. Just like we integrate velocity in order to find total distance, for this we want to make sure that we're integrating a rate to find the total volume in this case. We're only integrating from 0 to 25 because it was asking for the volume at the time that we found in part B, so that max volume time. So just from 0 to 25, and then we want to make sure that we add that 60,000 to it. That happened before we started sucking the oil up, started removing it. And part of this integral is reliant on part B, that 25 came from part B. But even if your part B is incorrect, you can still get full points here as long as this number came from part B. So if you need to make something up in part B so that you can use that number here, do that.